we're going to talk about Le Chatelier's principle as it relates to volume and temperature changes today, okay? So what I'm going to do is talk about volume and pressure first. You guys know that volume and pressure are inversely related. So, that's a bit thin. There we go. So V and P are inversely related. This was Boyle's law. So if we change the volume, and let's say I make the volume smaller, then that means that the pressure will subsequently increase. And in order to get back to equilibrium, you would have to relieve some of that added pressure. You will never relieve all of it, okay? So the two situations that we're going to encounter are solutions and gaseous mixtures. And I'll go over what happens with them. And likewise, if you increase volume, you decrease pressure, you would need to restore some of the lost pressure to help us get back to equilibrium. So here it says that a system at equilibrium will respond to volume changes by shifting to relieve some, I'm going to emphasize some, of the added pressure or to replace some of the lost pressure. Okay, when we're dealing with solutions, the type of pressure that exists in solutions is called osmotic pressure. You guys probably briefly talked about it in biology, and I'm really not going to go any deeper into it than that. But you also know that when we're dealing with pressures of gases, when we're dealing with individual gases that are part of a mixture, we're looking at their partial pressures. So let's take a look at the next page. And I'm going to look at the first example, which involves a gaseous mixture. So here I've got hydrogen and fluorine gases as my reactants, and then I have hydrogen fluoride gas as a product. So what you want to do is you want to count the coefficients on the reactant and the product side, and that will inevitably help you predict which direction you will shift based upon the volume changes. So here I've got two gases on the reactant side, and I also have two gases on the product side. So when the number of coefficients is the same, okay, for the gases, that means that if you change the volume, there is no way for you to like restore or relieve some of the added pressure because the number of gas particles is the same. So this type of equilibrium mixture will result in no observable change, okay? Let's take a look at a sample problem. Here we've got a gaseous mixture again. I've got two gases on the reactant side. And then I have one gas on the product side. Okay, so they're going to compress this system. So a compression means that we are decreasing the volume, which will cause what to happen to the pressure? Yeah, so the pressure will increase. Okay, so we need to relieve some of that added pressure. That means you will shift to the side with fewer gas particles. Okay, so since the right-hand side only has one gas particle, we're going to shift to the right. Now, another question that they're going to ask you is about the number of each type of molecule that's present, okay? So when you shift to the right, you're obviously going to increase the number of PCl5 molecules. So here it says PCl5 molecules will increase. And as I shift to the right, I'm consuming my PCl3 and Cl2 molecules. So that means the number of PCl3 and Cl2 molecules will decrease. Okay? The last question that they could ask you is related to concentration. So if they say, how does the concentration compare with the initial equilibrium? When you make a volume smaller, that means I have the same number of particles essentially occupying a smaller volume, which increases the concentration of everything. Does that make sense? So here it says, because the system was compressed, every substance has a higher concentration. Okay, let's take a look at the sample problem on the top of the next page. Okay, in this example, they are diluting it. Diluting something means that you're going to add water. When you add water, you're going to increase the volume of the container. So here I've got solutions. So I'm going to highlight these states of matter, and then I'm going to count the number of particles that are in solution. So I have 2 reactants, and then I have 1 product. So anytime you dilute something, what you're doing is, since this is a solution, we are going to decrease the osmotic pressure. Well, in order to restore equilibrium, I need to bring some of this osmotic pressure back. That means you need to shift to the side with more particles. Okay, so that's why we end up shifting to the left. And then they also want to know what will happen to the number of each type of particle. As you shift left, you consume product and you produce more reactant. So that means the number of HNO2 molecules will go down, and then the number of H+ and NO2 -1 ions will go up. Lastly, they want to know, how does the concentration of everything compare to before we had diluted the system? Well, when you diluted it, you made the volume larger, the concentration of everything dropped. Okay, so every substance has a lower concentration at the new equilibrium than it did initially. Okay, let's take a look at some practice problems. Okay, I'm going to have you guys do these. Okay, so here we're compressing. What does that mean we're doing to the volume? Yeah, volume goes down. So that means the pressure goes up. So I need to relieve some of that extra pressure that was added. Everything that we have here is a gas. I have 2 gases on the reactant side, 3 gases on the product side. Which direction would you shift? Yes, shift left, because left has fewer particles. Okay, and then when we shift left, we're going to increase the number of NaCl particles. You will decrease the number of NO and Cl2 particles. And then what happens to the concentration of everything? Yeah. Okay, for number 2, we diluted it. So a dilution means the volume increased. So that means the pressure came down. You need to restore some of that lost osmotic pressure. I'm highlighting all the states of matter. You have 1 particle on the reactant side, 3 particles on the product side. Which direction do you shift? Shift to the right, because there are more particles there. This will restore some of the lost pressure. So when you shift to the right, you will increase the number of silver ions and S2O3 negative 2 ions, and then you will decrease the number of reactant ions, okay? And then since you diluted it by adding a bunch of water, that means the volume is really, really large, and that means the concentration of everything took a dive. We good? Okay. All right, let's take a look at the next page. So in this problem, the volume was decreased. Does that really matter? Don't I have 2 gas particles on each side? There will be no observable change in this case. Okay, I can't relieve anything. Because when we decrease the volume, you increase the pressure. There's no way to relieve some of that added pressure. I can't shift to one side or the other in hopes of doing so. Okay? Okay, let's take a look at the effect on the forward and the reverse rates. Okay? So the direction with the greater sum of gaseous or aqueous reactant coefficients is going to be more sensitive of the 2 directions to volume changes. Okay, so if we take a look at this example here, I'm highlighting all of my states of matter. I have 2 particles on the reactant side and 1 particle on the product side. So if you go ahead and you dilute this by adding a bunch of water, then what will happen is we're going to shift to the side with more particles. So you would shift left. Agreed? Okay. So diluting this will actually decrease the forward rate more than the reverse rate, because the sum of the coefficients for the forward reaction is 2, and you have 1 on the product side. The reverse reaction only has 1. Okay, so anytime you make the volume bigger, the rate will slow down. It's just a matter of which one is going to slow down more. Okay, so just count the coefficients for something like that. If you take a look at this other reaction down here, this is a gaseous reaction, and here I've got 2 gases on the reactant side and 2 on the product side. Again, there would be no disruption to this because we have the same number of particles on each side. And then let's look at, is there one more example or no? No. Let's go to the next page. Let's take a look at these 2 examples. Here I've got a gaseous reaction mixture again. I have 3 particles on the reactant side, 2 on the product side. They want to know what happens to the rates when I decrease the volume. When you decrease the volume, you're going to notice that the rates are actually going to increase for both of them. So if we decrease the volume, we're going to cause a greater increase in the forward rate than the reverse rate because you have more particles on the reactant side. During that stress, you can see here that the forward rate has taken a huge leap in comparison. When you get back to the second equilibrium, then you can see both rates increase, but now they are the same. And then let's take a look at the other example at the bottom of the page. Down here, they are diluting it, so they're adding water to make the volume bigger. Anytime you, oops, wrong one. Anytime you dilute something, the rates are going to drop. It's just a matter of which one drops more. Here I'm highlighting all of my states of matter. I have 2 on the reactant side, 1 on the product side. So what will happen here is since the forward rate has more coefficients, you will decrease the forward rate more than the reverse rate. And you can see that during the stress here, the forward rate dropped a lot more. And then when you restored equilibrium, those 2 rates both dropped. Now they're the same value. Let's take a look at the next page. Let's look at some practice problems.